Good morning. I'm Ms. Michek, and I'm going to be talking about the ideal gas law. Before we can talk about the ideal gas law, though, we need to talk about what an ideal gas is. So, ideal gases are those gases whose particles do the following things. So, before we can talk about that, we need to talk about exactly what kind of particles we're talking about. So, particles of a gas. So, particles, meaning that from our first couple of units, particles are things like atoms. And if we're specifically talking about a gas, if we're talking about atoms, we're probably talking about the noble gases. So things like neon or argon. Other types of particles we might talk about are things like molecules. And we might have molecules of things like nitrogen, hydrogen, oxygen. Remember, these are our diatomics. And we could have molecules of things like methane or carbon dioxide. All of those are molecules. Okay, so when we're referring to these types of particles, this is what we're referring to. Okay, or these are examples of things that we're referring to. So they take up no space. They have no intermolecular forces. So thinking back to our bonding chapter, now remember that intermolecular forces are not bonds. Intermolecular forces are the bonds between molecules. So if a nitrogen and a nitrogen were to come in close contact with each other, that would be an intermolecular force. So these would have no intermolecular forces at all. And they follow all gas laws under all conditions of temperature and pressure. So you might be looking at this and going, I don't know about all that. So no gas is truly ideal because no gas takes up zero space, okay? If it's a molecule, even though it's really, really tiny, it takes up some space. Also, they could have some intermolecular forces. They might have some London forces when they pass by each other. Some might even have some dipole-dipole forces if they are polar molecules. Okay? So, and they don't all follow all gas laws under all conditions of temperature and pressure. So we're going to talk about some conditions where they may not follow all of the gas laws under all conditions of temperature and pressure. Okay. So, why do we actually have this law if not all gases are truly ideal? Well, most gases behave like ideal gases under most temperature and pressure situations. Okay? Most temperature and pressure situations, like normal temperature and pressure situations, they're going to behave like an ideal gas. Okay? They're not going to have very many intermolecular interactions. They are so small that we can make approximations as if they took up no space, and under normal situations of temperature and pressure, they behave as the gas laws say that they should. And so we can make calculations using the ideal gas law and make closely approximated measurements. All right, so when are the situations where they do not behave like gases, basically? Well, at extremely high pressures and extremely low temperatures. If the temperature gets low enough or the pressure gets high enough, we really don't have a gas anymore. Okay, if we compress that gas and we make the pressure high enough or the temperature low enough, we actually start to get into a liquid situation and we don't have a gas anymore. All right, so I want to talk about what the ideal gas law is before we get into some problems. All right, so our ideal gas law uses the relationship between volume, pressure, temperature, and the number of moles. So that's kind of new for us. The ideal gas law is this: PV equals nRT. And I want to show you that it is in your reference packet on page 3. So if you look right here, there's your ideal gas law in case you ever forget it. And you might be wondering, hey, you're leaving out R. That is the ideal gas constant. There are actually 3 of those, and they depend on the unit of pressure that we use. So I'm going to talk about that for just a minute before you can watch the next video with a couple of practice problems. And N is the number of moles. So there are 3 values for R, and they depend on which unit of pressure you're given. If you're given pressure in the problem in atmospheres, then you are going to use 0.0821 for your R value. If you are given your pressure in kPa, then you are going to use 8.314. If you are given your R value in millimeters of mercury, then you are going to use 62.4 as your R value. And you might be wondering, do I have to memorize that? No, you do not. That is on the front of your reference packet. And it says gas constant, R. Okay, so you have 0.0821 liters times atmospheres over moles times Kelvin, 62.4 liters, millimeters of mercury, divided by moles times Kelvin, and 8.314 liters times kPa, divided by moles times Kelvin. So, if or when you go to put these into a problem, one thing I always get asked is, do I need to use all of the units? Yes, if you were given your pressure in millimeters of mercury, when you go to plug in R, you would plug in 62.4 liters times millimeters of mercury divided by moles times Kelvin. And that would be your entire R value. And that's the beginning of the ideal gas law. You can watch the next video for a couple of practice problems.